They said it looked like a pile of junk when Technical Sergeant Eddie Sparks Kowalski started wiring together vacuum tubes, copper coils, and crystal fragments he'd salvaged from shot-down aircraft around the airfield. The Army Air Forces had spent millions developing sophisticated radio navigation systems that were supposed to guide bomber formations safely back to base, but Eddie knew the official equipment had a fatal weakness: it failed completely when atmospheric conditions turned bad, leaving hundreds of bombers lost in the fog with nowhere to land. Eddie had grown up in the steel mills of Pittsburgh, where his Polish immigrant father had taught him that the best solutions came from understanding how things really worked, not how they were supposed to work. On March 17, 1944, over the skies of England, Eddie was about to prove that a steelworker's son with a gift for electronics could build a radio beacon system that would outperform millions of dollars in military research and bring 200 lost American bombers safely home through the worst weather conditions of the war. What happened next would revolutionize military aviation navigation, challenge everything the experts thought they knew about radio technology, and demonstrate that sometimes the most reliable innovations come from someone willing to ignore the rulebook and build what actually works. If stories like this fascinate you, make sure to hit that subscribe button. These accounts reveal how American ingenuity and individual brilliance achieved what entire research departments couldn't accomplish. The thick fog that rolled in from the North Sea on the afternoon of March 17, 1944, transformed the peaceful English countryside into a grey nightmare that stretched from the Channel coast to the Scottish Highlands. Visibility dropped to less than 50 feet in some areas, and radio-atmospheric conditions became so unstable that standard navigation equipment began failing across the entire British Isles. At RAF Bassingbourn, home base for the 91st Bomb Group, Technical Sergeant Eddie Kowalski stood in the radio repair shop and listened to increasingly desperate radio transmissions from B-17 Flying Fortress bombers trying to find their way home from a daylight bombing mission over Germany. The bombers had completed their mission successfully, but now they were lost in fog so thick that pilots couldn't see their own wingtips, let alone identify landmarks or airfields. Eddie, 26 years old from Pittsburgh, Pennsylvania, had been responsible for maintaining and repairing radio equipment for the 91st Bomb Group since arriving in England 8 months earlier. His background was different from most Army Air Forces radio technicians. Before the war, he had worked as an electrician in the steel mills of Pittsburgh while spending his evenings as an amateur radio operator, experimenting with long-distance communications and building his own radio equipment from scratch. The skills Eddie had learned in his father's basement workshop, understanding how electrical circuits really worked, how to improvise solutions with available materials, and how to troubleshoot complex problems under pressure, had made him the most sought-after radio technician in the 8th Air Force. Pilots trusted Eddie to keep their radio equipment working under the most challenging conditions, because he understood not just how to follow repair manuals, but how to fix problems that the manuals didn't cover. But now, listening to the confused and increasingly panicked radio calls from bombers circling somewhere in the fog above England, Eddie realized that the problem wasn't with individual radio sets, it was with the entire navigation system that the Army Air Forces used to guide bombers back to their bases. The standard radio beacon system worked perfectly under normal conditions, but it became unreliable or completely useless when atmospheric interference disrupted radio signals. On days like today, when fog and atmospheric conditions made visual navigation impossible, the official navigation equipment left bomber crews flying blind with no way to find their bases before they ran out of fuel. Eddie had an idea for a solution, but it would require building a radio beacon system that violated several Army Air Forces regulations and ignored most of the established principles of military radio technology. The innovation born from desperation. Eddie's idea was based on his experience as an amateur radio operator, where he had learned that reliable long-distance communication often required adapting equipment and techniques to specific atmospheric and geographical conditions rather than relying on standardized approaches that might not work under all circumstances. The official Army Air Forces radio beacon system used high-frequency transmissions that provided excellent range and clarity under normal conditions, but became unreliable when atmospheric disturbances interfered with radio propagation. Eddie's solution was to build a low-frequency beacon system that would remain stable and reliable even under the worst atmospheric conditions. The technical challenge was that low-frequency radio required much larger antennas and more powerful transmitters than were normally available at individual airbases. Eddie's solution was to create a distributed antenna system using existing structures around the airfield, metal buildings, fuel tanks, and even aircraft themselves, as components of a massive antenna array that could generate the low-frequency signals needed for reliable navigation. The transmitter design was equally innovative. Instead of using a single high-powered transmitter that might fail under stress, Eddie planned to build multiple smaller transmitters that would work together to create a redundant beacon system. If one transmitter failed, the others would continue operating, ensuring that the navigation signal remained available even if individual components were damaged or malfunctioned. But perhaps most importantly, Eddie's system would use a different approach to encoding navigation information. Instead of the complex digital codes used by official equipment, Eddie's beacon would transmit simple, distinctive audio signals that pilots could identify and follow even if their radio equipment was partially damaged or operating under degraded conditions. Eddie knew that building this system would require materials and components that weren't available through official supply channels, and techniques that weren't covered in any Army Air Force's technical manual. He would have to scavenge components from damaged aircraft, improvise construction methods, and test his system under real-world conditions while bombers were actually lost in the fog. The most challenging aspect was that Eddie had only a few hours to build and deploy his system before the bombers circling overhead would run out of fuel and be forced to attempt emergency landings in fields and forests across England. The desperate construction that defied regulations. As radio calls from lost bombers became increasingly urgent, Eddie began the most intense engineering project of his life. Working with a small team of volunteer mechanics and radio operators, he started assembling his improvised beacon system using whatever materials could be found around the airbase. The antenna system required connecting dozens of metal structures across the airfield into a single, coordinated array. Eddie's team ran hundreds of yards of wire between buildings, vehicles, and aircraft, creating a web of electrical connections that transformed the entire airbase into a giant radio antenna. The transmitter components came from salvaged radio equipment that had been removed from damaged bombers and fighter aircraft. Eddie had been collecting these components for months, intending to use them for spare parts, but now he combined them into a multi-transmitter system that could generate the low-frequency signals his beacon required. The power system was perhaps the most challenging aspect of the construction. Low-frequency radio transmission required much more electrical power than standard radio equipment, and the airbase's electrical system wasn't designed to handle the load that Eddie's beacon would demand. His solution was to connect multiple aircraft generators in parallel, using the electrical systems of grounded bombers to power his improvised navigation beacon. The signal encoding system was elegantly simple. Instead of complex navigation codes, Eddie's beacon would transmit a distinctive audio pattern, a series of long and short tones that spelled out the airbase's call sign in Morse code. Pilots could identify this signal even through static and interference, and could use standard radio direction finding techniques to navigate toward the source of the transmission. But the most critical aspect of Eddie's system was the calibration and testing process. The beacon had to be precisely tuned to ensure that pilots could use their existing radio equipment to receive and interpret the navigation signals. This required real-time testing with aircraft that were actually flying in the fog, using the desperate radio calls from lost bombers as test signals to verify that the system was working correctly. As Eddie and his team worked frantically to complete the beacon system, radio calls from the lost bombers revealed that fuel levels were becoming critically low. Several pilots reported that they had less than 30 minutes of flying time remaining, and some crews were already discussing preparations for emergency bailouts over the English countryside. The race was on to complete Eddie's improvised navigation system before 200 American airmen were forced to abandon their aircraft and parachute into the fog-shrouded landscape below. The first transmission that saved lives. At 1,647 hours, with daylight fading and bomber fuel levels reaching critical minimums, Eddie activated his improvised beacon system for the first time. The massive antenna array he had constructed across the airfield began transmitting the distinctive Morse code signal that identified RAF Bassingbourn and provided navigation guidance for lost aircraft. The initial response was immediate and dramatic. Within minutes of the beacon's activation, bomber pilots began reporting that they were receiving a strong, clear navigation signal that cut through the atmospheric interference that had been disrupting their official radio equipment. Lieutenant Robert Ace Patterson, pilot of a B-17 bomber that had been circling in the fog for over 2 hours, was the first to successfully use Eddie's beacon for navigation. "This is incredible," Patterson radioed. "I'm getting a signal that's stronger and clearer than anything we've had all day. Following the bearing now." Using standard radio direction finding techniques, Patterson was able to navigate directly toward Eddie's beacon, breaking through the fog just as his bomber appeared over RAF Bassingbourn with less than 10 minutes of fuel remaining. The landing was successful, and Patterson's crew became the first airmen to be saved by Eddie's improvised navigation system. But Patterson's bomber was just the beginning. As word spread among the lost bombers that a reliable navigation signal was available, aircraft from across the fog-bound region began turning toward Eddie's beacon. The low-frequency signal proved capable of penetrating atmospheric interference that had made other navigation systems useless, providing clear guidance for bombers flying at altitudes and distances that exceeded the range of conventional radio beacons. The distinctive Morse code signal that Eddie had chosen proved to be exactly the right approach for the conditions. Pilots could identify and follow the beacon signal even when their radio equipment was partially damaged or operating under degraded conditions. The simplicity of the signal meant that navigation was possible using basic radio direction finding techniques that every pilot had learned during training. Within the first hour of operation, Eddie's beacon had guided 18 bombers safely back to RAF Bassingbourn. The success rate was remarkable, with every aircraft that attempted to use the beacon succeeding in finding the airfield and landing safely despite fuel levels that were often critically low. The psychological impact on the bomber crews was equally important. Pilots who had been facing the prospect of emergency bailouts or crash landings suddenly had a reliable means of navigation that gave them confidence and hope. Radio communications that had been filled with panic and desperation were replaced by calm, professional coordination as crews worked together to follow Eddie's beacon home. The beacon that revolutionized navigation. As Eddie's improvised system continued to guide bombers safely through the fog, word of its success spread throughout the 8th Air Force command structure. Other airbases began requesting information about Eddie's techniques, hoping to establish similar beacon systems that could provide reliable navigation during adverse weather conditions. The performance characteristics of Eddie's beacon exceeded the capabilities of official Army Air Force's navigation equipment in several important areas. The low-frequency signal remained stable and reliable under atmospheric conditions that rendered high-frequency systems useless. The distributed antenna system provided signal coverage over a much wider area than conventional radio beacons. The redundant transmitter design ensured continuous operation even if individual components failed. Most importantly, Eddie's system was compatible with existing aircraft radio equipment, requiring no modifications or special training for pilots and radio operators. The simplicity of the signal encoding meant that navigation was possible using techniques that every airman already knew, making the system immediately useful without requiring extensive retraining or equipment changes. But perhaps the most remarkable aspect of Eddie's innovation was its cost-effectiveness. The entire system had been built using salvaged components and improvised construction techniques, at a total cost that was probably less than a single day's operation of the official research and development programs that had produced the standard navigation equipment. By the end of the day, Eddie's beacon had guided 200 bombers safely back to RAF Bassingbourn, with several additional aircraft being directed to nearby airfields that had established their own improvised beacon systems based on Eddie's techniques. The success rate was unprecedented. Every aircraft that had attempted to use the beacon system had successfully navigated to a safe landing, despite weather conditions that would normally have resulted in numerous emergency landings and probable casualties. The achievement was particularly remarkable given the severe fuel limitations that many of the bombers were experiencing. Several aircraft landed with less than 5 minutes of fuel remaining, indicating that Eddie's beacon had provided navigation guidance that was accurate enough to bring aircraft directly to their destination airfields without wasted time or fuel spent searching for landing sites. The success of Eddie's improvised navigation system during the March 17 emergency established him as the leading expert on radio beacon technology in the 8th Air Force, but it also raised questions about why official equipment had failed so completely under conditions that Eddie's homemade system had handled without difficulty. The recognition that challenged military doctrine. The success of Eddie's improvised radio beacon system attracted attention from the highest levels of Army Air Forces command, including officers responsible for navigation equipment development and procurement. The fact that a single technician using salvaged materials had created a navigation system that outperformed millions of dollars in official equipment raised serious questions about military research and development priorities. Colonel James Morrison, commanding officer of the 8th Air Force Communications Division, was dispatched to study Eddie's techniques and assess their potential for wider implementation throughout American air operations in Europe. Colonel Morrison had a background in electrical engineering and had been involved in developing some of the standard navigation systems that Eddie's beacon had outperformed. Morrison's initial reaction to Eddie's system was amazement at the sophistication of the design and the effectiveness of the results achieved using improvised construction methods and salvaged components. Sergeant Kowalski, this system would be impressive if it had been developed by our best research laboratories. The fact that you built it in one afternoon using scrap materials is extraordinary. Eddie's response was characteristically modest. Sir, I just used what I learned building radios back home and adapted it for what we needed here. The principles aren't complicated if you understand how radio waves actually behave under different conditions. Morrison spent several days testing Eddie's beacon system and studying his construction techniques. The testing revealed that Eddie's approach solved several fundamental problems that had plagued official navigation equipment for years. The low-frequency design provided reliable signal propagation under atmospheric conditions that disrupted higher-frequency systems. The distributed antenna concept provided signal coverage and reliability that exceeded conventional beacon designs. The redundant transmitter architecture ensured continuous operation under conditions that would disable single point-of-failure systems. Perhaps most importantly, Eddie's techniques could be implemented quickly and inexpensively using materials that were available at any airfield, making reliable navigation available to units throughout the Army Air Forces rather than limiting it to bases with expensive specialized equipment. Morrison's report to 8th Air Force Headquarters recommended immediate adoption of Eddie's techniques throughout American air operations, with provisions for training programs that would teach radio technicians how to build and maintain improvised beacon systems using locally available materials. The training that spread the innovation. Eddie was temporarily assigned to the 8th Air Force Communications Training Center in London, where he was tasked with developing standardized procedures for teaching improvised radio beacon construction to communications specialists throughout the European theater. The assignment presented unique challenges, since Eddie's techniques were based on intuitive understanding of radio principles and practical experience with improvised construction methods rather than formal engineering training. The solution was to create training programs that combined Eddie's practical techniques with theoretical explanations that helped other technicians understand the principles behind his innovations. The training emphasized understanding the relationship between radio frequency, atmospheric conditions, and signal propagation, teaching students how to analyze local conditions and adapt beacon designs to achieve optimal performance under specific operational requirements. Students learned to evaluate available materials and modify construction techniques based on what components and facilities were available at their particular bases. Eddie also taught advanced techniques for optimizing beacon systems for different aircraft types and operational patterns. Students learned to adjust signal characteristics and antenna configurations for bombers versus fighters, day versus night operations, and different weather patterns that affected radio propagation. The program produced communication specialists who could not only build their own beacon systems but also troubleshoot and improve existing equipment, spreading Eddie's innovations throughout American air operations in Europe and eventually to other theaters of operation. But perhaps most importantly, the training programs emphasized the principle that effective radio communication required understanding the real-world conditions that affected signal propagation, rather than relying on theoretical models that might not account for local environmental factors. The legacy that transformed military aviation. Eddie Kowalski's radio beacon innovations continued to influence military aviation navigation long after the end of World War II. His principles and methods were incorporated into official military doctrine and became standard elements of communications training for subsequent conflicts. The fundamental insights Eddie had developed. That reliable navigation required adapting radio systems to specific atmospheric and geographical conditions, that redundant distributed systems were more reliable than single high-powered transmitters, and that simple signal encoding was often more effective than complex digital systems, became core principles of modern military communications. His techniques were adapted for use with different aircraft types and in different environments, from helicopter operations in Vietnam to cargo flights in the Arctic. The basic approach of using locally available materials to create mission-specific communications equipment became standard practice for special operations units and remote detachments. During the Cold War, Eddie's innovations influenced the development of navigation systems for both military and civilian aviation, with particular emphasis on backup systems that could provide reliable navigation when primary equipment failed or was jammed by enemy action. The principles Eddie had pioneered also influenced civilian applications of radio navigation technology, from maritime communications to emergency services and disaster relief operations. His understanding of how radio systems could be adapted to local conditions proved valuable for any application that required reliable communication under challenging environmental conditions. After the war, Eddie returned to Pittsburgh where he used his military experience and radio expertise to establish a successful electronics business that served both civilian and military customers. His company specialized in custom communications equipment for applications that required reliable performance under challenging conditions. Eddie received the Distinguished Flying Cross for his contributions to Allied air operations in Europe, recognition that was unusual for ground personnel but reflected the life-saving impact of his innovations on bomber crews throughout the 8th Air Force. The bomber crews who had been guided safely home by Eddie's beacon system never forgot the radio technician whose improvised equipment had saved their lives. Many maintained contact with Eddie for years after the war, and several naming their children after the man whose ingenuity had brought them safely through the fog. The human stories behind technical achievement. Behind the technical accomplishments and military recognition of Eddie's radio innovations were human stories that illustrated the profound impact of individual creativity and determination on the lives of fellow service members and the success of military operations. The 200 bomber crewmen who were guided safely home by Eddie's beacon system on March 17, 1944, represented 2,000 individual lives that were saved by one man's refusal to accept the limitations of official equipment. These were sons, fathers, brothers, and husbands who returned safely to their families because Eddie had the knowledge and courage to build something better than what the Army had provided. Lieutenant Robert Patterson, the first pilot to successfully use Eddie's beacon, later wrote, "I honestly don't think we would have made it home that day without Eddie's radio. We were down to fumes and completely lost in the fog. When that signal came through, clear and strong, it was like hearing the voice of God." Eddie didn't just save our aircraft, he saved 10 lives in our crew and probably hundreds of others. The psychological impact on bomber crews throughout the 8th Air Force was equally significant. Airmen who had previously worried about navigation failures during bad weather gained confidence knowing that reliable backup systems were available when official equipment failed. This confidence translated into more effective operations and better mission completion rates. Eddie's relationship with the air crews he supported was characterized by mutual respect and professional dedication. Pilots and radio operators appreciated Eddie's commitment to developing solutions that actually worked under combat conditions, rather than simply maintaining equipment according to regulations that might not address real operational needs. For Eddie, the most important measure of success was not technical recognition or military awards, but the knowledge that his work was bringing American airmen home safely. The personal satisfaction Eddie gained from solving practical problems with creative solutions motivated him to continue refining and improving his techniques throughout the war. This commitment to continuous improvement and practical effectiveness became a model for other military innovators who understood that the best solutions often came from understanding real-world problems and developing creative approaches to solving them using available resources. The relationship between individual initiative and collective success that Eddie's story illustrated became an important example of how military effectiveness could be enhanced through the creativity and determination of individual service members who were willing to challenge conventional approaches and develop better solutions. The enduring principles of practical engineering. The broader significance of Eddie Kowalski's story extends beyond military radio technology to fundamental questions about innovation, problem-solving, and the relationship between theoretical knowledge and practical application. Eddie had demonstrated that effective solutions often required combining scientific principles with hands-on experience and creative adaptation to specific operational requirements. His success was based on understanding that laboratory-designed equipment and real-world applications could produce very different results, and that effective systems needed to be optimized for actual operating conditions rather than theoretical scenarios. Eddie's approach required deep understanding of radio principles, but it also required practical skills in construction, materials evaluation, and environmental adaptation. The principles Eddie applied, careful analysis of operational requirements, creative use of available materials, and continuous refinement based on practical results, proved relevant to many fields beyond military communications. His techniques demonstrated that sophisticated capabilities could be achieved without expensive equipment or formal research facilities, provided that the designer understood the underlying principles and was willing to experiment with innovative approaches. Eddie's story illustrated the importance of combining different types of knowledge and experience when addressing complex problems. His background in industrial electronics and amateur radio provided insights that formal military training had missed, demonstrating that innovation often comes from bringing diverse perspectives and skills to bear on challenging problems. Perhaps most importantly, Eddie Kowalski had shown that individual initiative and creative thinking could achieve results that large-scale research and development programs had failed to accomplish, provided that the individual understood the problem thoroughly and was willing to experiment with unconventional solutions using whatever resources were available. So here's the question Eddie's story poses: in your own field, what limitations are you accepting that might be overcome through creative application of fundamental principles and innovative use of available resources? What knowledge and skills from other areas of your experience might provide insights that conventional approaches have overlooked? And do you have the confidence to experiment with unconventional solutions when conventional equipment and methods aren't providing the results you need? Eddie Kowalski proved that sometimes the most effective innovations come not from research laboratories and engineering departments, but from practical people who understand problems intimately and are willing to apply fundamental principles in creative ways to achieve specific objectives using whatever materials and knowledge are available to them.